speaker also, so I'll just introduce myself. So my name is Varun. I'm a postdoc researcher at the University of Groningen, and I'm working on hydrogen unreturn, so basically looking into atomistics. And I work with Professor Erik on the Giessen and Francesco Maresca. So if you look at the energy motivation, so it's always nice to quantify what are the renewable and what are the conventional energy sources. And when you consider the conventional energy sources, we look at natural gas, oil and coal. So you see the amount of carbon dioxide which is being produced per the energy of megajoules. And you see that the renewable sources, there are several alternatives which are hydrogen, and additionally you have solar, wind and nuclear. But out of all of the renewable sources, green hydrogen is very attractive because it's not only a fuel, but it can be directly used as a feedstock. And since there is a lot of momentum gaining into the green steel making community now, where you can directly use hydrogen for steel making. So green hydrogen is something which is a newer source of energy. And apart from that, in terms of my hometown right now, there is a Groningen, there's a big project there which is based called North H2. So the main motivation of this project is to have green hydrogen, so produce hydrogen by renewable sources, and then transport this existing green hydrogen using the existing gas pipelines which are there in the country. And these gas pipelines are based on Iceland low alloy steels. But then the question comes at what is the interaction of hydrogen with steel? And when we look into the hydrogen interaction with steel, it reduces into an embrittlement which is known for several decades. And this is a catastrophic failure which occurs and can have lifetime consequences. But this is a continuum scale more what we see. But when we zoom a bit later into the atomistic scale, you see that what happens is hydrogen is a very tiny atom, and it diffuses very fast interstitially through the lattice of the host metals. But apart from the diffusion, it can also get trapped at the defect. So basically, you have a vacancy here, and hydrogen can go towards the vacancy and form a hydrogen vacancy cluster. But at the same time, so that same cluster can attract more hydrogen and create nanovoids. And basically, you see that here there's a missing four vacancies are missing, and then the hydrogen goes there and make a nanovoid formation. And the kinetics of this interaction of hydrogen with the defects is what governs actually the entire behavior. So for example, here you look at the stress strain behavior of an X100 grade. So for a very uncharged, you have a very high elongation. So a lot of energy under this curve. But as you charge for longer times, 3, 6, and 12, so more and more hydrogen gets trapped into the lattice, and as a result, you have a loss of ductility. In terms of the mechanisms, Varun has shown several mechanisms which are all proposed based on the defects. So I'll just quickly run through them. So the first one that you have is called hydrogen enhanced decohesion, which is Erik. And the main principle is hydrogen interacts with the crack. Okay? So basically it reduces the surface energy near the crack surfaces, and it's easier for the crack to fill in a brittle manner. The second one is hydrogen enhanced localized plasticity, which deals with the mobility of the dislocations. So it's known that hydrogen enhances the mobility of dislocations. And the third one is the hydrogen, when it goes into the lattice, the strain of the hydrogen is such that it displaces an atom from its natural position, creating a self-interstitial atom and a vacancy. And this vacancy is actually what hydrogen strain-induced vacancy is the mechanism, and you can have nanovoid formation. Recently, Professor Deshpande has published a work which is on hydrogen-induced fast fracture, where they talk about phase transformation, so from BCC to HCP, and you have a hydride formation, which is also known for basically an intermittent formation. And then Varun argued a bit more about the different mechanisms that you can have dislocations at the crack tip, but you can create more dislocation at the same time, and then this can lead to higher stresses near the crack tip and ultimately a failure. But there is no clear consensus on these mechanisms, that which mechanism operates at what time scale and what time scale. And since when we talk about fracture, the main thing is the energy dissipation near the crack. And here we need to look at the role of dislocations, how the dislocations interact with the hydrogen. And this is what my work deals with, one part of my work deals with, that is I want to understand what are the micromechanisms of hydrogen and dislocation interaction, and then from there have a physics motivated theory. So what I do is actually, since the interaction of hydrogen with defects is a multi-scale problem, time and space, you can choose several levels, and there have been several models proposed for hydrogen entanglement. But we focus mostly on the atomic scale, so basically DFT and molecular dynamics. And today I show the results from the molecular dynamics and statics simulations where how the hydrogen interacts with the dislocation. And from that you can look at the mobility, how does hydrogen affect the mobility of the dislocation, obtain a mobility law which can be fed upscale towards the discrete dislocation classification. So to begin with, let's look at the hypothesis of the hydrogen localized plasticity, a mechanism where the hydrogen is said to increase the mobility of the dislocations causing localized plasticity. So there are two ways, if we imagine a lattice, if you have hydrogen, there are two things that can happen. Hydrogen can either pin the dislocation or it can make mobile. This is not clear how it makes it mobile. So we can actually compare the unpinning stresses of the dislocations to get more insight into this mechanism. And this is exactly what I do here. So what we do is we create an edge dislocation. So here all the blue atoms that you see are the iron atoms. There's the BCC lattice. The one in here, this region in the center is the edge dislocation core. And the red atoms between the planes are the hydrogen atoms which are placed between the planes. And the top and the bottom surfaces you see which are white are actually free surfaces. And there are some areas where you see white colors in between. These are iron atoms which are actually distorted due to the tetragonal distortion of the hydrogen, causing actually breakdown of the BCC symmetry, local BCC symmetry. And why do I consider edge dislocations is because if you look at the work of Ren, edge dislocations are highly mobile. So even at 0K, they are very fast to move. They move very fast, and in tungsten you can see that in any BCC metal you can see that now it's getting more clear and clear that the edge dislocations are actually what govern the plasticity at lower temperatures in a highly deformed material structure. In terms of simulation details, what I do is I have a hydrogen which is distributed randomly. So I put randomly the hydrogen at tetrahedron interstitial sites. And then we apply periodic boundary condition on the x and the y. So basically here the x, which is into the plane, is the dislocation line direction. The y-axis is basically the dislocation glide direction, and the z-axis is the normal to the dislocation. So it's basically a BCC slip system. And we use an embedded atom iron hydrogen potential, in this case from Ramasubramanian. So to start with the results, I do a molecular statics, basically, which is a 0K deformation. With a 0.5 atomic hydrogen percent concentration. And here you can see that as you start applying stress, the dislocation does not move. There's a very small movement of dislocation. But as you, this dislocation does not move because there's a hydrogen atom pinning it. And then when you keep on increasing the stress, the dislocation glides. And then it encounters another hydrogen environment. And then it gets pinned again. And then you need to increase the stress again for it to unpin. So basically, for comparison, if you take a pure iron case, you have a flow stress where the dislocation would glide around 72 megapascal. But in the case of when you add hydrogen into the case, the pile stress, which is the unpinning stress, is of the order of 450 megapascal. And the flow stress, which means the stress for the dislocation to glide towards the end of the boundary, is of the order of 560 megapascal. And here you can see there's a jerky motion that the hydrogen moves, that the dislocation glides, then it gets stopped again, then it moves again. So basically, here what we observe is a hydrogen-assisted pinning. So we have a strengthening theory. So we don't see that the hydrogen increases the mobility of the dislocation. So this was only one random trial. So what we do is actually we create a complement. So we run 20 simulations per concentration to create a statistics of the random distribution. So here all the hydrogen is distributed randomly in different instances. And the main outcome from this graph is basically you see that with higher concentrations you have very high pile stress of the order of 700 megapascal. But there's something interesting. What happens is for very low concentrations, which is 10 ppm, there are some realizations of hydrogen distributions where you have very high values of the order of 400 megapascal, which means that the unpinning stress of the pile stress gets governed by the local distribution, how the hydrogen is distributed around the dislocation and the dislocation core. So more information we can get from the box plot actually. So you take this data and create a box plot, and in this box plot you see that in this left you have the pile stress, which is the unpinning stress, and on the right, which is the flow stress. The main point you should see is the green dots in this blocks plots, which are here, which are the mean values of the stress of the either the piles or the flow. And you can see that with the increasing hydrogen concentration, the pile stress or the flow stress keeps on increasing, which means that the more the hydrogen you have in the lattice, there's going to be more hardening or more strengthening of your material. Second part was that right now I showed that I do random configuration of hydrogen and just do 0K deformation. But then the question occurs, since the dislocation code is a very attractive towards for the hydrogen, so the hydrogen has a tendency to aggregate towards the core. So what we do is we do run anti-simulations. At 500K, I start with the lattice where the hydrogen is randomly distributed, and then we do the anti-simulation. We run at 500K for 10 nanoseconds. And what you see is that all the hydrogen moles in the lattice is actually goes towards the core, and it gets really all of the hydrogen actually now located near the tensile region of the dislocation. So everything gets accumulated over there. And this is interesting, and this comes because of the core has an attractive interaction around this area. So hydrogen prefers to stay near the dislocation core. So from random, we go to a cluster configuration where we do diffusion study at a high temperature. Then the second point comes, we can use this configuration that we get to do deformation or to apply shear. And that is what I do in the next part, that I take the cluster configuration and then apply a deformation at 0K. And what happens is basically I only show a snapshot of around 2.5 gigapascal. So nothing happens up to 2.5 gigapascal. So the dislocation is actually pinned. So the hydrogen forms a corporal atmosphere around the dislocation. And then when you exceed a plate stress of 2.5 gigapascal, the dislocation flags freely. So that is actually the unpinning stress for it. And you can do this for all the different simulations. So we do the same statistical sampling. We run simulations for all the different configurations, and then what you get is similar plot what I showed before for random one. But now here the scales get changed, and the trend is similar. That you have quite a significant increase in the pile stress as well as the flow stress, and the amount is almost 6 to 7% times the random configuration. And it gets much more clear when you compare the random versus the clustered in a log scale on the x-axis. So for the random configuration, you see that the values keep on increasing, whereas for the clustered configuration, what you observe is that at very high concentrations, there's a bit of a saturation occurring. So which means that there's a two linear regime. So if I plot this on the log scale, I may get a power law from two different regimes. So here at very high concentration, you have a saturation, which means that after a certain point, the hydrogen concentration does not matter in the dislocations. And just coming to the conclusion part, so I showed that the short edge dislocation, basically there's a getting of the dislocation due to hydrogen, and this leads to strengthening. And the extent of the strengthening is governed by two things, that is the amount of the local hydrogen concentration near the dislocation, and the second is what is the distribution of the hydrogen atoms, that is whether they're randomly or they're clustered near the core. And so basically, based on the statics based results that I have, that we observe that hydrogen does not actually help basically. So it does not increase the mobility of the dislocation in this case. Of course, we have further stuff to do. That is, we need to consider the effect of the finite temperature on the hydrogen induced strengthening. By finite temperature, I mean diffusion and deformation at the same temperatures, and what would be the extent and the global distribution there. And the second part is that we want to actually look into the effect of dislocation wavelength, and what is the characteristics wavelength of these dislocations, and what is the effect of hydrogen concentration on that. And based on that, we want to develop an analytical model for strengthening of interspecies, where we actually can predict the critical resolved phase stress as a function of finite temperature, local hydrogen concentration, and the strain rate directly without doing any simulations. And that was my presentation. If there are any questions, we'll be happy to answer.
Actually, to me, it looks like the strengthening effect is very good. You have some barriers to dislocation, and then above certain level of stress nearby. That looks actually very good. So what is the problem? Why don't we like it?
So first of all, this is a mechanism which has been quite debatable. Actually, this has been a well-established theory in the equation, which is hydrogen localized plasticity. So we don't find that it increases the mobility. So first of all, the point was whether it decreases the mobility of the dislocations or not, and how does it increase it, right? The second point is how does it cause embrittlement, that is the second point. So hydrogen has an effect on the surface energies. So right now I just consider the edge dislocations, but you can also have screw dislocations. And for screw dislocations, most of the potentials that you have in the literature, they predict the wrong core structure. So the core structure of the dislocation is wrong, and the Piles energy barrier is also completely wrong. So basically, this is what I'm saying. So, and this is also the second part of my work, that we are developing new iron and hydrogen machine learning based potentials. So basically, if you look at this EM potential, which is a mandate one, you see a double hung behavior. Whereas if you have a DFT based material, so you see the Piles barrier, it's only a single hung. Whereas so gap is the one that we are using right now for machine learning. And then we want to actually get to the embrittlement part. So how does it affect the surface energies also using this